Good morning. I am Aditi studying in BSc Chemistry Honors first year. Today we are reading chapter number 2 of Organic Chemistry, Mechanism of Organic Reactions. So we start. Introduction. During a chemical reaction, reactant molecules are converted into product molecules. The arrangement of atoms in the product molecules is altogether different from that present in reactant molecules. This change, which is brought about by redistribution of electrons, usually occurs through some definite steps. A detailed step-by-step description of a chemical reaction showing as to how reactant are converted into product is called reaction mechanism. In this unit, we shall study some important aspects of organic reaction mechanism. Arrow notations in organic reactions. Organic reactions usually involve making and breaking of covalent bonds. A covalent bond is often represented by a dash, and the movement of a pair of electrons is shown by a curved arrow. The movement of a single electron, on the other hand, is shown by a fish hook arrow or half-headed arrow. For example, you can see this. In these notations, the tail of the arrowhead indicates the site from where the electron pair or single electron has to move, and head indicates the side to which it has to move. In contrast, double-headed arrows do not indicate the movement of electrons but are used to separate various canonical structures. For example, benzene may be regarded as the resonance hybrid of two Kekule first and second and three Dior third to fifth structures. Types of bond fission. Organic reactions occur through making and breaking of bonds. There are two ways in which covalent bonds can be broken. These are homolytic fission, heterolytic fission. Homolytic symmetrical fission, when a covalent bond joining two atoms A and B breaks in such a way that each atom of the covalent bond takes away one electron of the shared pair, it is called symmetrical cleavage or homolytic fission, or simply homolysis. The neutral chemical species such as A and B, which contain an odd or unpaired electron and which are produced by homolytic fission of covalent bonds, are called free radicals. Homolytic fission usually occurs in non-polar bonds and is favored by high temperatures, gas phase or pyrolysis, or under the influence of ultraviolet light (UV) radiations, and by the presence of radical initiators such as peroxides. Heterolytic unsymmetrical fission, when a covalent bond joining two atoms A and B breaks in such a way that the both electrons of the covalent bond shared pair are taken away by one of the bonded atoms. The mode of bond breaking is called unsymmetrical cleavage or heterolytic fission, or simply heterolysis. Heterolytic fission is usually indicated by a curved arrow which denotes a two electron displacement. For example, as shown above, heterolytic fission results in the formation of ionic species, that is, cations and anions. Further, heterolytic fission usually occurs in polar bonds and is favored by polar solvents. Quite often, the ionic species formed by heterolytic fission carry the positive or the negative charge on carbon atoms. Such ionic species are called carbon cations or carbon anions, respectively, according as the carbon carries positive or negative charge. It may be emphasized here that the same covalent bond can undergo homolytic or heterolytic fission under different conditions. In general, the bond dissociation energies for homolytic fission are low while they are quite high for heterolytic fission. For example, reagents and substrates. We know that whenever an organic reaction is carried out, we use certain starting materials called reactants. These are further classified as reagents and substrates. Actually, there is no clever-cut distinction between these two terms because each one of them cannot react in the absence of the other. In general, a more reactive reactant is called the reagent, while the less reactive reactant is called the substrate. A substrate may more precisely be defined as the reactant which contains carbon atoms, some of whose bonds with other atoms are broken, and some new ones are formed as a result of the reaction with the reagent. For example, in the reaction ethylene bromide. Ethylene is the substrate and bromine is the reagent. Types of reagents. Reagents are broadly classified into two types: electrophilic reagents or electrophiles, nucleophile reagents or nucleophiles. Electrophiles or electrophilic reagents. Electrophilic reagents or electrophiles. Electro is equal to electro and phile is equal to love. Are electron loving chemical species. Their lust for electron is due to presence of electron deficient atom in them. Electrophiles are of two types: positive electrophiles. Electrophiles in which the electron deficient atom carries a positive charge are called positive electrophiles. For example, proton H positive, hydronium ion H3O positive, bromonium ion Br positive, chloronium ion Cl positive, carbonium ions R positive, nitronium ion NO2 positive, benzene diazonium cation C6H5N2 positive, anilinium ion C6H5NH3, etc. Neutral electrophiles. Electrophiles in which the electron deficient atom does not carry any charge are called neutral electrophiles. For example, free radicals are carbenes X2C, nitrines, boron, trifluoride BF3, aluminium chloride AlCl3, ferric chloride FeCl3, stannic chloride SnCl4, etc. In BF3, AlCl3, FeCl3, etc., the central atom has only 6 electrons in the valence shell and thus has a strong tendency to acquire a pair of electrons to complete its octet. However, in case of SnCl4, the central atom has the required octet of electrons in the valence shell but still has a strong desire to accept more electrons because of the presence of vacant d orbitals in it. Since both positively charged and neutral electrophiles are short by a pair of electrons, they have a strong tendency to seek electrons from other sources and thus behave as Lewis acids due to their attraction for electrons. Electrophiles always attack the substrate molecules at the site of highest electron density. B. Nucleophiles or nucleophilic reagents. Nucleophilic reagents or nucleophiles. Nucleo is equal to nucleus, phile is equal to love, are nucleus loving chemical species. Since the nucleus of any atom is positively charged, therefore nucleophile must be electron-rich chemical species containing at least one unshared or lone pair of electrons. These are of two types. Negative nucleophiles. Nucleophiles which contain an unshared pair of electrons and are also negatively charged are called negative nucleophiles. For example, halide ion, Cl, Bri, etc., hydroxide ion, alloxide ion, anide ion, cyanide ion, carbon ions, hydride ion, carboxylate ion, acetylide ion. Neutral nucleophiles. Nucleophiles which contain an unshared pair of electrons but carry no charge are called neutral nucleophiles. For example, water, ammonia, amines, alcohols, ethers, thioalcohols, hydroxylamine, Grignard reagents, alkyl or arylithiums, lithium aluminium hydride, sodium borohydride, etc. Since both neutral and negatively charged nucleophiles contains at least one lone pair of electrons, they have a strong tendency to donate this pair of electron to electron deficient atom or species and hence behaves as Lewis bases. In other words, nucleophiles always attack the substrate molecules at the site of least electron density. Some of the important characteristics of electrophilic and nucleophilic reagents are summarized below. Electrophilic reagents, nucleophilic reagents. Electron deficient species accept an electron pair from the substrate, act as Lewis acids, poses as empty orbital to accept electrons from the substrate molecule, are either neutral or positively charged chemical species. Electron-rich species donate an electron pair to the substrate, act as Lewis bases, poses at least one lone pair of electrons which can easily be donated to the substrate molecule, are either neutral or negatively charged chemical species. Types of organic reactions. All the organic reactions can be broadly classified into following 7 types: substitution reaction, addition reaction, elimination reaction, condensation reaction, rearrangement reaction, isomerism reaction, pericyclic reactions. Substitution reactions. A substitution reaction is that which involves the direct replacement, displacement, or substitution of an atom or a group of atoms in an organic molecule by another atom or group of atoms without any change in the remaining parts of the molecule. The incoming group gas attached to the same carbon to which the outgoing group was attached. The product obtained as a result of substitution is called the substitution product, and the new atom or group of atoms which enters the molecule is called a substituent. Depending upon the nature of the attacking species, nucleophile, electrophile, or a free radical, the substitution reactions are of the following three types. Nucleophilic substitution reactions. Substitution reactions which are brought about by nucleophiles are called nucleophilic substitution reactions. In all these reactions, a stronger nucleophile usually displaces a weaker nucleophile. These reactions are typical of alkyl halides. For example, hydrolysis of an alkyl halide with an aqueous base to give an alcohol. Hydroxide ion, alkyl halide, alcohol, substitution product, halide ion, weaker nucleophile. Electrophilic substitution reactions. Substitution reactions which are brought about by electrophiles are called electrophilic substitution reactions. In these reactions, the attacking species is an electrophile and the leaving group leaves without the pair of bonded electrons. These reactions are typical of arenes and other aromatic compounds where the high electron density of the aromatic ring attracts the electrophiles. For example, halogenation, nitration, sulfonation, and Friedel-Crafts reactions. Benzene plus nitronium electrophile, nitrobenzene substitution product. Free radical substitution reactions. Substitution reactions brought about by free radicals are called free radical substitution reactions. These are typical of alkanes and other saturated compounds. For example, chlorination of methane in presence of heat or diffuse sunlight to give methyl chloride and hydrogen chloride. Methane, methyl chloride. The reactions occur by a free radical mechanism which involves the following three steps: intonation, propagation, termination. Addition reactions. Reactions which involve combination between two reacting molecules to give a single molecule of the product are called addition reactions. Such reactions are typical of compounds containing multiple double and triple bonds depending upon the nature of attacking species, electrophile, nucleophile, or a free radical. Addition reactions are of the following three types. Nucleophilic addition reactions. Addition reactions brought about by nucleophiles are called nucleophilic addition reactions. These reactions are typical of aldehydes and ketones. For example, base catalyze addition of HCN to aldehydes or ketones. Ketone nucleophile, ketone cyanohydrin addition product. Electrophilic addition reactions. Addition reactions brought about by electrophiles are called electrophilic addition reactions. These reactions are typical of alkenes and alkynes, for example, addition of Br2 or HBr to propylene. Propylene isopropyl carbocation secondary 2-bromopropane addition product. Free radical addition reactions. Addition reactions brought about by free radicals are called free radical addition reactions. For example, addition of HBr to alkanes in presence of peroxides, propene and propyl bromide. The reactions occurs by the following mechanism: initiation, propagation, termination, peroxide, alkoxy free radical. Elimination reactions. An elimination reactions is one that involves the loss of two atoms or groups of atoms from the same or adjacent atoms of a substance, leading to the formation of a multiple, double or triple bond depending upon the relative positions of the atoms or groups eliminated. These reactions are classified as alpha, beta and gamma elimination reactions. Alpha elimination reactions. In these reactions, the loss of two atoms or groups occurs from the same atom of the substrate molecule. For example, base catalyze dehydrohalogenation of chloroform to form dichlorocarbene. Chloroform dichlorocarbene. Dichlorocarbene is the reactive intermediate involved in carbylamine reaction and Reimer-Tiemann reaction. B elimination reactions. In these reactions, the loss of two atoms or groups occurs from the adjacent atoms of the substrate molecule. For example, acid catalyze dehydrogenation of alcohols and base catalyze dehydrogenation of alkyl halides. Acid catalyzed dehydration of alcohols, ethanol, ethene. Base catalyzed dehydrogenation of alkyl halides, ethyl bromide, ethene. Gamma elimination. In these reactions, loss of two atoms or groups occurs from alpha and gamma positions 3 bonds away of the molecule, leading to the formation of three-membered rings, for example 1,3-dibromopropane cyclopropane. This reaction is called Freund reaction and is extensively used for the synthesis of three-membered rings. Condensation reaction. In these reactions, two or more molecules of the same or different reactants combine to form a product with or without the elimination of simple molecules such as H2O, HCl, NH3ROH, etc. For example, two molecules of acetaldehyde condense in presence of dilute alkali to form 3-hydroxybutanol. Since beta hydroxyl aldehydes or ketones are commonly known as aldols, therefore this reaction is called aldol condensation. Hydroxide ion base ethanol acetaldehyde carbon anion. 3-hydroxybutanol. Aldols on heating with dilute mineral acids undergo dehydrogenation to form alpha beta unsaturated aldehydes or ketones. Thus, 3-hydroxybutanol, buta-2-enol crotonaldehyde. Rearrangement reactions. Reactions involving the migration of an atom or a group from one atom to another within the same molecule are called rearrangement reactions. For example, dehydration of 3-methyl-butane-2-ol with concentrated H2SO4 occurs through 1,2 migration of hydride ions to give the rearranged product 2-methyl-butene. 3-methyl-butane-2-ol. However, when 2,2-dimethylpropan-1-ol is treated with concentrated H2SO4, it involves 1,2 migration of the methyl group to give the same rearranged product 2-methyl-butene, 2,2-dimethylpropan-1-ol. Hofmann-bromoamide reaction involving the conversion of 1-amides to 1-amines on treatment with Br2 in presence of KOH. Primary amine. In this rearrangement reaction, the group R migrates from carbon to nitrogen to first give an alkyl isocyanate, which upon hydrolysis gives a primary amine with one carbon atom or less than the original amide. Isomerism reaction. Reactions which involve interconversion of one isomer into another, keeping the molecular formula as well as the carbon skeletons of the reactants and the products intact are called isomerization reactions. For example, interconversion of trans-butene to cis-butene and vice versa may be regarded as geometrical isomerization reaction. Trans-butene, cis-butene. 1-bromobutane isomerizes 2-bromobutane in presence of anhydrous AlCl3 at 575 Kelvin. 1-bromobutane, 2-bromobutane. Pericyclic reactions. There are large number of organic reactions which do not involve ionic carbon cations, carbon anions, etc. or free radical intermediates. Instead, these reactions occurs in a single step view, a cyclic transition state. In these reactions, bond making and bond breaking occur simultaneously. These reactions do not require any catalyst and are initiated either by heat or light. All such reactions are called pericyclic reactions. For example, electrocyclic and cycloaddition reactions. Electrocyclic reactions involve conversion of acyclic conjugated dienes to cyclic alkenes and vice versa. Buta-1,3-diene cyclic transition state cyclobutane. Cycloaddition reactions. Cyclic transition state cyclobutane. Buta-1,3-diene. Acrolein cyclic transition state cyclohexene 1-carbaldehyde. The addition of a diene 4-pi electron system to a nucleophile 2 pi electron system to form a 6-membered ring is called the Diels-Alder reaction. Energy concentrations. The ultimate criteria of feasibility of any chemical reagent is given by Gibbs free energy change delta G, which is related to enthalpy change delta H and entropy change delta S by the relation delta G is equal to delta H minus T delta S. It should be noted that the reaction proceeds in the forward direction only when delta G is negative. A positive delta G, on the other hand, suggests that the reaction has a tendency to proceed in the backward direction. Further, since entropy S is a measure of the degree of randomness or disorder of a system, therefore a system is more stable when it has maximum entropy. On the other hand, reactions in which there is loss of randomness should not be favorable, and it has indeed been found that reactions involving a decrease in the number of molecular species in going from reactants to product proceed only if delta H is negative. Reaction is exothermic and also large enough to make delta G negative. Conversely, when the number of molecular species increases is in going from reactants to product, there is increase in the entropy of the system, and minus T delta S term becomes large enough to make the reaction move in the forward direction even when it is not an exothermic reaction. When the substances are taken in the standard state 273 Kelvin and 1 atmosphere pressure, the above equation may be written as delta G is equal to delta H minus T delta S dt. When superscript 0 is used to denote standard states and delta G is the differences in standard free energies of the products and the reactants. However, in case of equilibrium reactions, the equilibrium constant K is related to delta G by the following expression. It may be noted that K denotes the extent of a chemical reaction. A high value of K indicates that the reaction proceeds significantly in the forward direction. Collision theory. A chemical reaction is believed to take place through collision between the reactant molecules. The number of collisions that take place per second per unit volume of the reaction mixture is called collision frequency. At ordinary temperature and pressure, the value of collision frequency is so high in the gaseous reaction that if all the collisions were effective, result in the formation of the product, the reaction should be completed within a fraction of a second. However, in actual practice, this is not so because most of the chemical reactions are all slow and many of them do not take place even at room temperature. This may be explained as follows. Energy factor. For a collision to be effective, the colliding molecules must have a certain minimum amount of energy called threshold energy. Since at ordinary temperature and pressure, most of the reactant molecules do not have energy equal to the threshold energy in the ground state. They have to be supplied some extra energy so that their collisions may become effective. This minimum amount of extra energy, which must be supplied to the reactant molecules in the ground state so that their energy becomes equal to the threshold energy, is called the activation energy. Activation energy is equal to threshold energy minus energy of the reactants in the ground state. Evidently, lesser the activation energy, faster is the reaction, or greater the activation energy, slower is the reaction. Orientation factor of the probability factor. In some cases, it is found that even if a large number of colliding molecules have more energy than threshold energy, still the reaction is slow. This is due to the reason that at the time of collision, the reactant molecules do not have the proper orientation for reaction to occur. This is called orientation factor or the probability factor. Thus, from the above discussion, it follows that rate is equal to collision frequency into energy factor probability factor, where Z is the collision frequency, where P is the probability factor, is the energy of activation, and is the fraction of collisions with energy greater than E activation. Transition state theory. Transition state theory has been found to be more useful in understanding the mechanism of organic reactions. According to this theory, collision between the reactant molecules, say A and BC, lead to formation of a highly energy species called the activated complex or the transition states. This species lies at the top of the energy barrier, separating the reactants and the products. The activated complex is subsequently decomposes to give the products. In other words, reactants on their way to products pass through a transition state. These sequence of events are shown in energy profile diagram for a one-step reaction. The rate of reaction depends on the rate at which the reactants are converted into the transition state rather than an collision frequency as was postulated in the collision theory. Since the transition state is in equilibrium with the reactants and hence its concentration is determined by an equilibrium constant K, which is related to free energy of activation by the reaction, where delta H is the enthalpy of activation and S is the entropy of activation. The activated complex or the TS is not a true molecule since it contains partial bonds and the energy of the system is maximum. Its life is extremely short and hence it cannot be isolated. It finally decomposes to give the products A, B and C. Figure 2.1 Energy profile diagram for a single step reaction. The free energy of activation of the reaction, besides other factors, depends upon the strength of the B, C, and AB bonds. The stronger the BC bond, higher is the energy of activation, and conversely, stronger the AB bond, lower is the activation energy. Further, since the free energy of activation represents the energy barrier, it affects the rate of reaction. Higher the energy barrier, slower is the reaction, and conversely, lower the energy barrier, faster the reaction in constant delta G degrees thermodynamic quantity. It merely gives the difference in standard free energy of the reactants and the products and hence does not affect the rate of the reaction. We have discussed above energy profile diagram for one-step reactions, but many organic reactions occurs in two steps. In all such reactions, the intentionally formed transition state first decomposes into a relatively less energetic but more stable species than the activated complex. This chemical species, which is less energetic but more stable than the activated complex, is the reactive intermediate. This reaction intermediate finally gets converted into the product through another activated complex or the transition state. Thus, a two-step reaction occurs through two transition states if the free energy of activation of the first transition state is higher than that of the second. Then the intermediate readily gets converted into the products. The intermediate cannot be isolated. In such cases, the first step is the rate determining step of the reaction. Figure 2.2 Energy profile diagram for a two-step reaction with a reactive intermediate with a stable isolable intermediate. If, however, the free energy of activation of the second transition state is higher than that of the first, then the intermediate is quite stable and hence can be isolated. In such cases, the second step is the rate determining step of the reaction. In the light of the above discussion, a reaction may follow the following two paths. Path 1 substrate reagent transition state products. Path 2 substrate plus reagent transition state intermediate transition state second products. A detailed step-by-step description of a chemical reaction showing as to how reactants are converted into products is called the mechanism of the reaction. If a reaction involves simultaneous making and breaking of bonds without the formation of any intermediate, it is said to be a concerted reaction. Such a reaction occurs through a single transition state. On the other hand, if a reaction occurs in two or more steps with the formation of a reactive or isolable intermediate, it is said to be stepwise or non-concerted reaction. The number of transition states formed during a stepwise reaction is equal to the number of steps by which the reaction occurs. Thus, a two-step reaction has two transition states, of which the one having higher free energy of activation constitutes the rate determining step of the reaction. Difference between transition state and intermediate and Hammond's postulate. Intermediate are normal covalent molecules or ions possessing a definite geometry and can be isolated in many cases. Even when they are too unstable to be isolated, their properties can be studied spectroscopically. Alternatively, they can be trapped by substances which are known to react rapidly with them. The transition state, on the other hand, is not a formal normal covalent molecular ion since it has only partial bonds. The properties of the transition state can be studied in terms of Hammond's postulate, which states that for any single reaction step, the geometry of the transition state for the reaction resembles the site to which it is closer in free energy of activation. Thus, the transition states may be described as reactant like, product like, or intermediate like, according as its energy lies close to the reactant product or the intermediate. For example, for strongly exothermic reactions, the geometry of the TS resembles that of the reactants. Existing bonds are almost intact and the new bonds are very little formed. Conversely, for strongly endothermic reactions, the geometry of the TS resembles that of the products. This generalization also holds good when the reaction proceeds through intermediates. For example, it is a well-known fact that branching at the alpha carbon increases the rate of SN1 reactions. Generally, it is explained in terms of the stability of the carbocation intermediates, but the rate enhancement does not depend upon the stability of the carbocations. Rather, it depends upon the ease with which the transition state leading to the formation of carbocations is reached. It depends upon, in other words, in terms of Hammond's postulate, we can assume that the transition state is carbocation like, and any factor which stabilizes the carbocation also stabilizes the transition state. As a result, such a transition state is reached more readily by lowering the magnitude of delta G. Catalyze, Catalysis. Catalyst may be defined as a substance that changes usually increases the rate of a reaction without itself being consumed in the reaction. It first combines with one of the reactants, forming an intermediate compound which then decomposes or combines with the other reactant to produce the product, and the catalyst is regenerated. It is believed that a catalyst increases the rate of a reaction by providing an alternate path from reactants to products with a lower energy transition state. In other words, a catalyst always combines with the reactants in such a way that the energy of activation of the transition state of a catalyzed reaction is always lower than that of the transition state for corresponding uncatalyzed reaction. For example, consider the catalytic effect of iodide ion on the hydrolysis of methyl chloride by OH ions. The hydrolysis of CH3Cl by OH occurs in one step through a transition state and its rate depends on the nature of delta G. Transition state. Addition of I ion to the reaction mixture provides an alternate path involving a two-step mechanism in which CH3I is the intermediate. Figure 2.3. Progress of the reaction, free energy profile diagram for the uncatalyzed broken line and catalyzed solid line reaction. Since iodide ion is a good nucleophile as well as good leaving group, therefore the free energy of activation for both the transition states is lower than the corresponding uncatalyzed one-step reaction. It may be noted that only the rate of the reaction increases but delta G of the reaction remains unchanged by the addition of the catalyst. Competitive reactions, kinetic and thermodynamic control. There are a number of organic reactions in which a compound under a given set of conditions can undergo competing reactions to give different products. Consider, for example, compound that gives two products, thermodynamically controlled, kinetically controlled, B and C. Further, suppose that B is thermodynamically more stable than C, but C is formed faster than A. If neither reaction is reversible, C will be formed in larger amount since it is formed faster. Such a product which is formed faster because it has lower free energy of activation is called kinetically controlled. However, if the reactions are reversible, this will not necessarily be the case. In such a process is stopped well before the equilibrium is reached. The reaction will be kinetically controlled since more of the faster formed product C will be present. However, if the reaction is allowed to reach equilibrium, the thermodynamically more stable product B will be the predominant product or may even be the exclusive product formed. Under these conditions, the intentionally formed less stable C reverts to A more quickly than the more stable product B does so. Such a product which is formed slowly but because of its greater stability keeps on accumulating in the reaction mixture will till equilibrium is reached is called thermodynamically controlled product. For further details, refer to 1.2 versus 1 for addition to dienes in Unit 6.2. Reactive intermediates. Most of the organic reactions occur through the participation of certain chemical species which are generally short-lived and highly reactive. Therefore, these species cannot be isolated. Their involvement can only be detected either by spectroscopic methods or by trapping them with more reactive substrates. These short lived, highly reactive chemical species are called reaction intermediates or reactive intermediates. Some important examples of reactive intermediates are carbocations, carbanions, free radicals, carbenes, nitrines, arenes, and amines. Carbocations, chemical species carrying positive charge on a carbon which has only 6 electrons in its valence shell, are called carbocations or carbonium ions. Carbocations are short-lived, highly reactive chemical species. Since the carbon atom carrying the positive charge is electron deficient, has 6 electrons, and thus has a strong tendency to complete its octet by accepting a pair of electrons. Generation of carbocations. Carbocations are produced by heterolytic cleavage of covalent bonds in which the leaving group takes away both the bonding electrons of the covalent bond. Some of the reactions in which carbocations are formed are summarized below. Ionization of alkyl halides in polar system. Tert-butyl chloride, tert-butyl carbocation, alkyl chloride, alkyl carbocation, benzyl chloride, benzyl carbocation. By protonation of unsaturated compounds such as alkenes, carbonyl compounds, and nitriles. Alkene carbocation, carbonyl compound, nitrile. By protonation of alcohols followed by dehydrogenation. By diaminium of primary aliphatic amines with nitrous acid. By action of superacids on alkyl fluorides. Classification. Carbocations are classified as primary, secondary, or tertiary according as the carbon carrying the positive charge in primary, secondary, or tertiary in nature. Methyl carbocation having only one carbon is, however, regarded as a special case. Methyl carbocation, ethyl carbocation, isopropyl carbocation, tertiary butyl carbocation. Orbital structure. The carbocations are planar chemical species. The carbon atom carrying the positive charge is sp2 hybridized. The three sp2 hybridized orbitals of this carbon form three sigma bonds with three monovalent atoms or groups which lie in a plane and are inclined to one another at an angle of 120 degree. The unhybridized 2p orbital, which is perpendicular to the plane of the three sigma bonds, is however empty. Figure 2.4 Orbital structure of carbocations. Stability. Stability of carbocations can be explained on the basis of laws of electrostatics, which state that any factor which tends to disperse the positive charge by distributing it over rest of the molecule must stabilize the carbocation, while any factor which tends to intensify the positive charge must destabilize the carbocation. Where G is an electron donating group, it disperses the positive charge and hence stabilizes the carbocation. Where G is an electron withdrawing group, it intensifies the positive charge and hence destabilizes the carbocation. Ability of alkyl carbocations. The order of stability of simple alkyl carbocations follows the order secondary primary. This order of stability can easily explained on the basis of the following. Inductive effect. We know that alkyl groups have electron donating inductive effect plus I effect. Because of their plus I effect, they release electrons towards the positively charged carbon, thereby dispersing the positive charge. This dispersal of charge leads to the stabilization of the carbocations. Evidently, greater the number of such alkyl groups attached to the positively changed carbon, greater will be the dispersal of the positive charge and hence more stable will be the carbocation. Thus, a tertiary carbocation with three alkyl groups should be more stable than a secondary carbocation with two alkyl groups, which in turn should be more stable than a primary carbocation, one primary with one alkyl group, while methyl carbocation with no alkyl group will however be the least stable. Tertiary butyl carbocation, isopropyl carbocation, ethyl carbocation, methyl carbocation. Hyperconjugation effect. The stability of carbocation can also be explained on the basis of hyperconjugation. In general, greater the number of alpha hydrogen, greater is the number of hyperconjugative structures and hence more stable in the carbocation. Thus, tertiary carbocation with 9 alpha hydrogens and hence 9 hyperconjugative structures is more stable than isopropyl carbocation with 6 alpha hydrogens and hence 6 hyperconjugative structure, which in turn is more stable than ethyl carbocation with 3 alpha hydrogens and hence 3 hyperconjugative structures, while methyl carbocation with no hyperconjugative structures is the least stable. Thus, the order of stability of alkyl carbocations follows the sequence tertiary butyl isopropyl ethyl methyl carbocation. Tertiary butyl carbocation 9 alpha hydrogen and hence 9 equivalent hyperconjugative structures. Isopropyl carbocation 6 alpha hydrogen and hence 6 equivalent hyperconjugative structures. Ethyl carbocation 3 alpha hydrogen and hence 3 equivalent hyperconjugative structures. Steric effects. As discussed above, carbon cations are planar chemical species, but most of the compounds from which they are obtained have tetrahedral structures. Thus, in the formation of carbocations, bond angle between the group increases from about 109 degree 28 minute to 120 degree. In other words, the group move about. This moving away of the groups relieves some of the steric strain present in the starting compound. Evidently, greater the relief in the steric strain, more easily a carbocation is formed, since the extent of steric relief is expected to be maximum in the formation of a tertiary carbocation, followed by secondary and primary carbocations, and least in case of methyl carbocation. Therefore, the order of stability of the various carbocations follows the sequence tertiary, secondary, primary, methyl. Stability of unsaturated carbocations. Stability of carbocations in which the positively charged carbon is next to a double bond or a benzene ring can be best explained on the basis of resonance effect. For example, consider the following cases. Stability of alkyl and benzyl carbocations. Alkyl and benzyl cations are stabilized due to dispersal of positive charge through resonance as shown below. Resonance stabilization of alkyl carbocation. Resonance stabilization of benzyl carbocation. Evidently, larger the number of phenyl groups attached to the carbon atom, being the positive charge, greater is the delocalization of electron or dispersal of positive charge, and hence more stable in the carbocation. Thus, diphenyl methyl carbocation is more stable than benzyl carbocation due to greater number of resonating structures. Diphenyl methyl carbocation. Resonance structures of diphenyl methyl carbocation. 3 more such resonating structures. Triphenyl methyl carbocation is still more stable than diphenyl methyl carbocation due to still larger number of resonating structures. Triphenyl methyl carbocation 6 more such resonating structures. Triphenyl carbocation is so stable that its salts such as chlorates, fluorobromates, etc. can be isolated and stored indefinitely. Thus, the overall stability of benzyl, diphenyl methyl, and triphenyl methyl carbocations follows the order: triphenyl methyl carbocation, diphenyl methyl carbon cation, benzyl carbocation. Similarly, triphenyl cyclopropenyl carbocation is more stable than diphenyl cyclopropenyl carbocation, which in turn is more stable than phenyl cyclopropenyl carbocation. Triphenyl cyclopropenyl carbocation, diphenyl cyclopropenyl carbocation, phenyl cyclopropenyl carbocation. Effect of substitution on the stability of benzyl carbocations. Presence of electron donating groups such as R, OH, OR, NH2, NH4, Nr2, etc. at O and P positions of the phenyl group, the carbon atom bearing the positive charge tend to stabilize the substituted benzyl carbocation relative to benzyl carbocation by dispersal of positive charge due to plus R effect, hyperconjugation effect in case of R group of the substituent. Conversely, presence of electron withdrawing groups such as Cn, NO2, CHO, COR, COOH, COOR, etc. at O and P positions tends to destabilize the substituted benzyl carbocation relative to benzyl carbocation by intensification of positive charge due to R effect of the substituent. Thus, p-methoxybenzyl carbocation, benzyl carbocation, p-nitrobenzyl cation. Stability of tryptylum ion or cycloheptatrienyl cation. Tryptylum cation is unusually stable. This unusual stability is due to the reason that is an aromatic cation containing 6 pi electron, 2 pi electron from each of the 3 double bonds. These 6 pi electrons are completely delocalized over all the 7 sp2 hybridized carbons atoms as shown below, just in the same manner as the 6 pi electron are delocalized in benzene ring. Resonance structure of tryptylum ion. Actually, the tryptylum ion is so stable that its reaction with nucleophiles such as water, alcohols, etc. is very slow. Instability of cyclopentadiene cation like cycloheptatriene cation, cyclopentadienyl cation should also be stabilized by resonance since the carbon atom carrying the positive charge is conjugated with 2 double bond. Actually, this carbocation is highly unstable, and the reason for the instability is that it is anti-aromatic cation containing 4 pi electrons. This instability of anti-aromatic compounds can be explained on the basis of HMO diagram, which you will learn in semester 2. Stability of alkoxoalkyl carbocations. Carbocations in which the carbon atom bearing the positive charge is attached to a heteroatom carrying lone pairs of electrons such as oxygen, nitrogen, halogen, etc. are also stabilized by resonance. For example, because of resonance stabilization, methoxymethyl cation can be isolated as a stable solid. Stability of alkyl cations like alkoxyalkyl cations, alkyl cation are also stabilized by resonance. Although due to the presence of a positive charge on the more electronegative oxygen atom, the contribution of canonical structure second is far less than that of group first to the resonance hybrid, yet acetyl cation CH3CO is almost as stable as tert butyl carbocation. Instability of vinyl and phenyl carbocations. Carbocations in which the positive charge is located on the doubly bonded carbon atoms such as vinyl CH2CH and phenyl C6H5 cations cannot be stabilized by resonance since the sp2 orbital of the carbon atom carrying the positive charge is perpendicular to the p orbitals of the double bond. As such, these are very short-lived chemical species. However, vinyl cations are more stable than methyl carbocation but less stable than primary carbocation as discussed below. Relative stability of carbocations. The relative stability of carbocations can be easily measured through heterolytic bond dissociation energy. The lower the value of heterolytic bond dissociation energy, greater is the stability of the carbocation. The heterolytic bond dissociation energy of some alkyl aryl halides are given in table 2.1. Table 2.1, heterolytic bond dissociation energy of some alkyl aryl chlorides in kilojoule mole inverse. From the above table, it follows that tertiary butyl carbocation, benzyl, isopropyl, alkyl, N-propyl, ethyl, vinyl, phenyl, methyl shifts in carbon cation or 1,2 rearrangement or carbon cations. 1,2 shifts are very common in carbon cation chemistry. The driving force for the rearrangement is usually the formation of more stable carbon cations since the energy difference in solution between a tertiary and a secondary and between a secondary and a primary carbon cation are about 11 to 15 kilocalorie mole inverse, 46 for 63 kilojoule mole inverse each. Therefore, these rearrangements are exothermic. These rearrangements either involve 1,2 hybrid shift or 1,2 methyl shift. 1,2 hybrid shift N-propyl carbon cation primary less stable, isopropyl carbon cation secondary more stable. Isobutyl carbon cation primary less stable, tert butyl carbon cation 3 secondary more stable. 3-methyl 2-butyl carbocation secondary less stable, 2-methyl 2-butyl carbon cations tertiary more stable. 2,2-methyl shift neopentyl carbon cation primary less stable, 2-methyl 2-butyl carbon cation tertiary more stable. 3,3-dimethyl 2-butyl carbon cation secondary less stable. 2,3-dimethyl 2-butyl carbon cation tertiary more stable. The new carbon cation thus formed can subsequently undergo nucleophilic substitution by reacting with a nucleophile or can undergo elimination by losing a proton from the adjacent atom. Carbon anions. Chemical species carrying a negative charge on carbon are called carbon anions. In these species, the carbon atom carrying the negative charge has 8 electrons in the valence shell, 6 from 3 covalent bonds and 2 from the lone pair of electrons. The carbon anions, like carbon cations, are also short-lived, highly reactive chemical species even though the carbon atom carrying the negative charge has an octet of electrons. The stability of carbon anions is believed to be due to the presence of a formal charge on them. Generation of carbon anions. Carbon anions are produced by hydrolytic cleavage of a covalent bond in which the leaving group departs with 3-methyl 2-butyl carbocation secondary less stable, 2-methyl 2-butyl carbocation tertiary more stable, 2,2-methyl shift neopentyl carbocation primary less stable, 2-methyl 2-butyl carbocation tertiary more stable, 3,3-dimethyl 2-butyl carbocation secondary less stable, 2,3-dimethyl 2-butyl carbocation tertiary more stable. The new carbocations thus formed can subsequently undergo nucleophilic substitution by reacting with a nucleophile or can undergo elimination by losing a proton from the adjacent atom. Carbon anions. Chemical species carrying a negative charge on carbon are called carbon anions. In these species, the carbon atom carrying the negative charge has 8 electrons in the valence shell, 6 from 3 covalent bonds and 2 from the lone pair of electrons. The carbon anions, like carbocations, are also short-lived, highly reactive chemical species. Even though the carbon atom carrying the negative charge has an octet of electrons, the instability of carbon anions is believed to be due to the presence of a formal charge on them. Generation of carbon anions. Carbon anions are produced by hydrolytic cleavage of a covalent bond in which the leaving group departs without the bonding electron of the covalent bond. This implies that every carbon anion has one lone pair of electrons which it can donate. Therefore, carbon anions may be regarded as Lewis bases or nucleophiles. These are usually generated by the following methods: by abstraction of hydrogens from the carbon atoms alpha or nitrocyano or carbonyl groups with a strong base, for example nitromethane, resonance stabilized anion, ethoxide ion, acetonitrile resonance stabilized anion, acetaldehyde resonance stabilized anion. By abstraction of hydrogen of terminal acetylenes with a strong base amide acetylene acetaldehyde ion. By addition of nucleophiles to alpha beta unsaturated carbons compounds, ethoxide ion, acrylonitrile resonance stabilized anion. Classification of carbon anions. Carbon anions are classified as primary, secondary, or tertiary according as the carbon atom carrying the negative charge is primary, secondary, or tertiary in nature. Methyl carbon anion containing only carbon is, however, regarded as a special case. Methyl carbon anions, ethyl carbon anion, isopropyl carbon anion, tert butyl carbon anion. Orbital structure of carbon anions. The structure of simple alkyl carbon anions is usually pyramidal, just like that of ammonia. The carbon carrying the negative charge is sp3 hybridized. 3 of the 4 sp3 hybridized orbitals form 3 sigma bonds with monovalent atoms or groups, while the fourth sp3 orbital contains the lone pair of electrons. Figure 2.5. Orbital structure of carbon anions. Since the lone pair, bond pair repulsion are expected to be greater than bond pair repulsions, the bond angles in carbon anions are much less than the regular tetrahedral angle of 109 degree 28 minute. In other words, carbon anions do not have the regular tetrahedral geometry but have pyramidal structure in which the bond angles are in between 97 degree to 100 degree. Even substituted carbon anions of the type R1, R2, R3C are optically inactive. If the sp3 orbital containing the lone pair of electron is considered as the fourth substituent, then carbon anions of the type R1, R2, R3C, because of their pyramidal shapes should be optically active and hence resolvable, but in actual practice, such types of carbon ions have never been resolved. To explain this, it has been assumed that pyramidal structure of carbon ions is not rigid but undergoes rapid inversion like ammonia molecule figure 2.6. Figure 2.6, inversion of carbanions, inversion of ammonia. As a result, one enantiomer gets rapidly converted into another enantiomer. Say second, ultimately a racemic mixture is obtained which cannot be resolved. Carbon anions can also have planar geometry. It has been discussed above that the shape of simple alkyl carbon anions is pyramidal. However, when the lone pair of electrons on the carbon atom carrying negative charge is conjugated with a multiple bond, then the carbon ions are always planar. This is due to the reason that these carbon ions are stabilized by resonance, and for resonance to occur, it is essential that the lone pair of electrons must be in a p orbital so that it can overlap with the p orbitals of the pi bond. Figure 2.7, planar structure of alkyl carbon ion. Thus, in alternate planar structure, the carbon atom carrying the negative charge is sp2 hybridized. Some other examples of planar carbon ions are benzyl carbon ion, diphenyl methyl carbon ion, triphenyl methyl carbon ion, and all other carbon ions obtained by abstraction of an alpha hydrogen atom from a carbonyl compound, for example, acetaldehyde carbon ion, ethyl acetate carbon ion. Stability. Like carbocations, stability of the carbon anions can be easily explained on the basis of inductive and resonance effect. Inductive effects. The stability of simple carbon ions follows the sequence methyl primary, secondary and tertiary carbon ions. Methyl carbon ion, ethyl carbon ion, isopropyl carbon ion, tertiary butyl carbon ion. This order of stability is exactly reverse of that of carbocations discussed above and free radicals discussed later in this unit, and can be easily explained on the basis of inductive effects as discussed below. Due to electron releasing inductive effect plus I effect of the alkyl groups, the intensity of the negative charge on the central carbon atom increases. This intensification of negative charge leads to the instability of carbon ion. Evidently, greater the number of alkyl groups attached to the carbon atom bearing the negative charge, greater will be the intensification of the negative charge, and hence more unstable will be the carbon ion. Thus, the methyl carbon ion with no alkyl group should be the most stable, followed by ethyl carbon ion with one methyl group and isopropyl carbon ion with two methyl groups, while tertiary butyl carbon ion with three methyl groups should be the least stable. Types of hybridization. The relative stability of the carbon ions derived from alkynes, alkenes, and alkanes can be explained on the basis of type of hybridization of the carbon carrying the negative charge. For example, sp hybridized carbon, sp2 hybridized carbon, sp3 hybridized carbon. As the s character of the carbon carrying the negative charge increases, the stability of carbon ion increases since the electrons are closer to the nucleus and hence of lower energy. Resonance effects. Carbon anions in which the unshared pair of electrons is present on the negatively charged carbon is attached to a multiple bond or a phenyl group are much more stable than simple alkyl carbon anions. This is due to the reason that these carbon anions are stabilized by resonance. Stability of alkyl and benzyl carbon ions. Alkyl and benzyl carbon ions are stabilized by dispersal of negative charge through resonance as shown below. Resonance stabilization of alkyl carbon ion. Resonance stabilization of alkyl benzyl carbon ion. Evidently, larger the number of phenyl groups attached to the carbon atom bearing the negative charge, greater is the delocalization of electrons or dispersal of negative charge, and hence more stable is the carbon ion. Thus, diphenyl carbon ion is more stable than benzyl carbon ion due to greater number of resonating structures. Diphenyl methyl carbon ion, 3 more such resonating structures. Triphenyl methyl carbon ion is still more stable than diphenyl methyl carbon ion due to still larger number of resonating structures. Effect of substituents on the stability of benzyl carbon ions. Presence of electron donating groups such as R, OH and H2 etc. at O and P positions of the phenyl group, the carbon bearing the negative charge tends to destabilize the substituted benzyl carbanion relative to benzyl carbanion by intensification of the negative charge due to plus R effect, hyperconjugative effect in case of R group of the substituent. Conversely, presence of electron withdrawing groups such as CnNO2, CHO, COR, COOH, COOR, etc. at O and P positions needs to stabilize the substituted benzyl carbanion relative to benzyl carbanion by dispersal of the negative charges due to R effect of the substituent. Thus, P-nitrobenzyl carbanion, benzyl carbanion, P-methoxybenzyl carbanion. Stability of cyclopentadiene anion. Cyclopentadiene anion is unusually stable since it is an aromatic anion containing 6 pi electrons, 4 pi electrons from 2 double bonds plus 2 pi electrons of the unshared pair. These 6 pi electrons are completely delocalized on all the 5 sp2s hybridized carbon atoms are shown below just in the same way as the 6 pi electrons of benzene are completely delocalized over all the 6 sp2 hybridized carbon atoms of the benzene ring. This dispersal of negative charge accounts for its unusual stability. Consequently, it has a high resonance energy 130 kJ mole inverse as compared to 151 kJ mole inverse of benzene, and hence cyclopentadiene anion is quite stable. Stability of carbanions carrying electron withdrawing groups such as CO, COR, NO2, CN, etc. tend to disperse the negative charge by resonance and hence increases the stability of the carbanions. For example, resonance stabilization of acetaldehyde carbanion, resonance stabilization of nitromethane carbanion. Further, larger the number of such groups, greater is the stabilization. For example, resonance stabilization of acetoacetic ester carbanion. Resonance stabilization of malonic ester carbanion, resonance stabilization of ethyl cyanoacetate carbanion. Free radicals. Chemical species carrying an odd or unpaired electron are called free radicals. For example, chlorine free radical, methyl free radical, phenyl free radical, benzyl free radical, triphenyl methyl free radical. Although free radicals are themselves electrically neutral, yet due to the presence of an odd electron, they are weakly attracted by the magnetic field and hence they are paramagnetic in nature. Like carbocations and carboanions, free radicals are also short-lived and highly reactive chemical species because of their tendency to acquire one more electron to complete the octet. Further, because of their tendency to acquire one more electron, free radicals may also be regarded as electrophiles. Generation of free radicals. Free radicals are generally prepared by homolytic fusion of covalent bonds either by heat or by light. For example, chlorine free radicals, benzoyl peroxide, phenyl free radicals, acyl free radical, alkyl free radical, teramethyl lead, methyl free radical. Classification. Free radicals like carbocations and carboanions are also classified as primary, secondary, and tertiary according as the carbon atom carrying the unpaired electron is primary, secondary, or tertiary in nature. Methyl free radical, ethyl free radical, isopropyl free radical, tertiary butyl free radical. Orbital structure. The alkyl free radicals are planar chemical species. The carbon atom carrying the odd electron is sp3 hybridized. The 3 sp2 hybridized orbitals of this carbon form 3 sigma bonds with monovalent atoms or groups which lie in a plane and are inclined to one another at angle of 120 degree. The unhybridized 2p orbital, which is perpendicular to the plane of these 3 sigma bonds, however, contains the odd electron. Figure 2.8. Orbital structure of free radicals. Stability. Like carbocations, the stability of free radicals can also be easily explained on the basis of hyperconjugation and resonance effect as discussed below. Hyperconjugation effects. Like carbocations, the stability of simple alkyl free radicals follows the sequence tertiary, secondary, primary, methyl. Butyl free radical, isopropyl free radical, ethyl free radical, methyl free radical. This order of stability can be easily explained on the basis of hyperconjugation effect. In general, greater the number of alpha hydrogens, greater is the number of hyperconjugative structures, and hence more stable is the free radical. Thus, tertiary free radical with 9 alpha hydrogens and hence 9 hyperconjugation structures is more stable than isopropyl free radical with 6 alpha hydrogens and hence 6 hyperconjugation structures, which in turn is more stable than ethyl free radical with 3 alpha hydrogens and hence 3 hyperconjugation structures, while methyl free radical with no alpha hydrogens has no hyperconjugative structures is the least stable. Tersh-butyl free radical 9 alpha hydrogens and hence 9 equivalent hyperconjugation structures. Isopropyl free radical 6 alpha hydrogens and hence 6 equivalent hyperconjugation structures. Ethyl free radical 3 alpha hydrogens and hence 3 equivalent hyperconjugation structures. Thus, the order of stability of alkyl free radicals follows the sequence tersh-butyl, isopropyl, ethyl, methyl free radical. Resonance effects. Free radicals which are stabilized by resonance are even more stable than simple alkyl free radicals. For example, alkyl and benzyl free radicals are stabilized by resonance through the delocalization of unpaired electron over the double bond or the benzene ring. Resonance structures of alkyl free radical. Resonance structure of benzyl free radical. Evidently larger the number of phenyl groups attached to the carbon atom carrying the unpaired electron, greater is the delocalization of electron and hence more stable in the free radical. Thus, diphenyl methyl free radical is more stable than benzyl free radical due to greater number of resonating structures. 3 more such resonating structures. Resonance structures of diphenyl methyl free radical. Triphenyl methyl free radical is still more stable due to still large number of resonating structures. 6 more such resonating structures. Resonance structures of triphenyl methyl free radical. Radicals in which the odd electron is located on a doubly bonded carbon atom such as vinyl CH2CH or phenyl C6H5 radical cannot be stabilized either by hyperconjugation or by resonance and hence are usually very short-lived. These radicals are even less stable than methyl free radicals as discussed below. Relative stability of free radicals. The relative stability of free radicals R can be measured through the homolytic bond dissociation energy D values of the RH bonds. The greater the value of bond dissociation energy, lesser is the stability of the free radical. Bond dissociation energy of some common RH bond at 298 Kelvin in kilojoule mole inverse, kilocalorie mole inverse. From the above table, it follows that the order of stability of different free radicals follow the sequence alkyl, benzyl, tersh, butyl, isopropyl, n-propyl, ethyl, methyl, vinyl, phenyl. Carbenes. Neutral divalent carbon species in which a carbon atom is bonded to two monovalent atoms or groups by covalent bonds and has two non-bonding orbitals containing two electrons between them are called carbenes. These are called methylenes. However, in actual practice, the parent species CH2 is called methylene, but its derivatives are commonly called carbenes. For example, methylene, dichlorocarbene, diphenylcarbene. Like carbocations, carbenes are short-lived, highly reactive chemical species since the central atom has only 6 electrons in the valence shell and thus has a strong tendency to complete its octet by gaining 2 more electrons. Thus, carbenes behave as Lewis acids or electrophiles. Typical reactions which involve carbene intermediates are carbyl-amine reaction and Reimer-Tiemann reaction. Generation of carbenes. These are generated by the following two methods: by thermal thermolysis or photochemical photolysis. Decomposition of cyclopropanes and oxyrenes. Phenyl cyclopropanes, methylene, phenylethane, 1,2-diphenyloxyrene. Phenyl carbene benzaldehyde. By thermal and photochemical decomposition of diazoalkane or ketones. Diazomethane, methylene or carbene, ketone, methylene. By the action of a strong base, usually pot-tersh butoxide on chloroform. Chloroform unstable dichlorocarbene. This reaction is an example of alpha elimination since H and Cl are lost from the same carbon atom. Type of carbenes. Depending upon the distribution of two non-bonding electrons between two orbitals, the carbenes are of the following two steps: singlet carbenes, triplet carbenes. If two non-bonding electrons are present in the one orbital, the two paired electrons are paired and the other orbital is empty. The carbene is said to be singlet carbene. A singlet carbene such as singlet methylene is usually represented as CH2. Since a singlet carbene has no unpaired electron, it has no dipole moment and hence it's diamagnetic. Being diamagnetic, it cannot be detected by electron spin resonance ESR spectroscopy. On the other hand, if the two non-bonding electrons are unpaired and are present in two different orbitals of equal energy with their spins parallel in accordance with Hund's rule, the carbene is said to be triplet carbene. A triplet carbene such as triplet methylene is usually represented as CH2. Unlike singlet electrons, it is paramagnetic and hence can be easily detected by ESR spectroscopy. Orbital structure. In the singlet carbene, the central carbon atom is sp2 hybridized. Two of the two sp2 hybridized orbitals are used in forming two sigma bonds with two monovalent atoms or groups, while the third sp2 orbital contains the two non-bonding structures electrons. The n-hybridized p orbital is however empty. Figure 2.9. Orbital structures of singlet and triplet carbenes. Thus, a singlet carbene is a bent chemical species. The structure of singlet carbene is similar to that of carbocation, since in both of them carbon is sp2 hybridized and one p orbital is empty. In the triplet carbene, the central atom is sp hybridized. Two of the sp orbitals form two sigma bonds with two monovalent atoms or groups, while the two unhybridized p orbitals py and pz are perpendicular to each other and contain one electron each. Figure 2.9. Thus, a triplet carbene is a linear species and behaves like a diradical or biradical. Stability. A triplet carbene is always more stable than the corresponding singlet carbene. This is due to the reason that is singlet carbene. The two non-bonding electrons are present in the same orbital and thus tend to repel each other. This inter-electronic repulsion increases the energy of the singlet state relative to the triplet state, in which the no bonding electrons are present in different orbitals. This is supported by the observation that triplet methylene is about 35.5 kJ, 8.5 kilocalorie in mole inverse, more stable than the singlet methylene. Further, carbenes in which the central carbon is attached to atoms, each one of which has a lone pair of electrons, are somewhat more stable than methylene due to resonance. Nitrines. Nitrines are the nitrogen analogues of carbenes. These are defined as neutral monovalent nitrogen species in which nitrogen has two unshared pairs of electrons and is bonded to only one monovalent atom or a group. Like carbenes, nitrines are also short-lived, highly reactive chemical species, since the nitrogen has only a sextet of electrons in the valence shell and thus has a strong tendency to complete its octet by gaining two electrons. Thus, nitrines, like carbenes, behave as Lewis acids or electrophiles. A well-known reaction which involves nitrine intermediate is Hofmann-bromamide reaction, which brings about the conversion of primary amides to primary amines containing one carbon atom less than the original amide. Primary amide, primary amine. Generation of nitrines. These are generated by the following methods: by thermal or photochemical decomposition of acids or isocyanates. Alkyl azide, alkyl nitrine, alkyl isocyanate, alkyl nitrine. By base catalyzed elimination of sulfonate ion from 0-hydroxyleamine 0-sulfonates. Types of nitrines. Like carbenes, nitrines are also of two types, singlet and triplet. In singlet nitrines, the four non-bonding electrons on nitrogen are present as two pairs, but in triplet nitrine, these are present in form of one pair and two unpaired electrons. Orbital structures. In the singlet nitrine, the nitrogen atom is sp2 hybridized. One of the sp hybridized orbital forms a sigma bond with a monovalent atom or group, while the other two sp2 orbitals contain a pair of electrons each. The unhybridized p orbital is, however, empty. Orbital structures of singlet and triplet nitrines. In the triplet nitrine, the nitrogen atom is sp hybridized. One sp orbital forms one sigma bond with a monovalent atom or a group, while the other contains a pair of electrons. The two unhybridized p orbitals py and pz are perpendicular to each other and contain one electron each. Figure 2.10. Stability and detection. Nitrines are too reactive to be isolated under ordinary conditions. Alkyl nitrines have been isolated by trapping in matrices at 4K, while aryl nitrines, being less reactive, can be trapped at 77 Kelvin. The trapping of nitrine is usually carried out by its reaction with carbon monoxide to yield isocyanides. Phenylizide, phenylnitrine, phenylcyano. 8. Arenes. Aromatic compounds containing a formal carbon-carbon triple bond are called arenes. The best known arene is benzene, which is aromatic analog of acetylene. In other words, it may be regarded as benzene minus 2 orthohydrogen and hence can be called as dihydrobenzene. Structure. The triple bond of benzene is altogether different from that of acetylene. In acetylene, it is made up of one sp-sp sigma bond and two pi bonds formed by sideways overlap of p orbitals. However, in benzene, the triple bond consists of one sp2 sigma bond and two pi bonds. One of the pi bonds is formed by the sideways overlap of two p orbitals, while the other is obtained by sideways overlap of two sp2 orbitals as shown in figure 2.11. This new pi bond lies along the side of the ring and hence has little interaction with the pi electron cloud lying above and below the aromatic ring, since the sideways overlap of sp2 orbitals is not good. Therefore, the new pi bond is very weak and hence benzene is a highly reactive molecule. Structure of benzene molecule. The sideways overlap of two sp2 orbitals forms a pi p bond out of the plane of the aromatic pi electron cloud. Generation and detection of arenes. By action of soda amide in liquid ammonia or aryl halides, benzene has been shown to be the intermediate in nucleophilic substitution reaction of aryl halides. For example, in presence of a strong base, aryl halides eliminate a molecule of HX form 0 positions to form arenes, which subsequently readily react with the available nucleophiles to form the substitution product. Bromobenzene, benzene, aniline, elimination, addition. This mechanism is called either benzene mechanism or elimination addition mechanism. Similarly, the intermediacy of benzene in the Dawes method for the industrial production of phenol from chlorobenzene and strong alkali has been demonstrated using chlorobenzene. Chlorobenzene, benzene, phenol, phenol. By thermal decomposition of benzene diazonium 2-carboxylate anthranilinic acid, benzene diazonium 2-carboxylate benzene. Detection. Arenes are usually detected either through mass spectrometry or by chemical reactions such as dimerization or cycloaddition reactions with substances like furan. Benzene, dibenzene, cyclobutane, benzene, furan, 1,4-epoxy 1,4-dihydropethylene reactions. The most important reactions of arenes are nucleophilic additions and cycloaddition reactions. The nucleophilic addition reactions N-alkyl aniline, benzene phenol, cycloaddition reactions benzene acryl nitroyl 1,2-benzo,3-cyclobutane. Enamines. Enamines are alpha, beta, and saturated amines. En plus amine. These are formed when an aldehyde or a ketone containing alpha hydrogen atoms reacts with a secondary amine in presence of a trace amount of an acid such as lysosulfonic acid (PTS), aldehyde or a ketone, secondary amine, carbonyl amine, unstable enamine. The equilibrium is shifted in the forward direction by removing H2O as an azeotrope with benzene. The secondary amines and most commonly employed in enamine formation are pyrrolidine, piperidine, or morpholine. Reaction of enamines. Some important reactions of enamines are discussed below. Alkylation and alkylation of ketones. Amines serve as useful intermediates in the alkylation and alkylation of ketones. Thus, when an amine is treated with an active alkyl halide such as allylic, benzylic, propyric, alpha haloether, alpha haloester, etc., alkylation occurs at the beta carbon atom of the amine. The hydrolysis of the amine salt thus formed gives the alpha alkylated ketone, for example, cyclohexanone, pyrrolidine, amine, imine salt, 2-benzyl cyclohexanone. This reaction is called Stork-amine reaction and exclusively gives monoalkylation product of the ketone. Therefore, it has the advantage over base catalyzed alkylation of ketones, which cannot be stopped at the monoalkylation stage and usually gives a mixture of products. Another advantage is that alkylation usually takes place on the less substituted side of the ketone, for example, 2-methyl cyclohexane 1 enamine 2-benzyl 6-methyl cyclohexane. The reason for the reduced selectivity is that the amine is stabilized by resonance between the p orbital containing the lone pair of electrons on the n atom and p orbitals of the double bond. This requires coplanarity of the bonds on the unsaturated carbon atoms and the nitrogen atom, which is possible in structure first but not in structure second due to steric hindrance. No steric hindrance. Similarly, alkylation of ketones can be carried out using acid chlorides instead of alkyl halides, amine acetyl chloride 2-acetyl cyclohexanone. Michael type reaction. Amines also react with alpha beta unsaturated ketones to first give Michael type adducts, which open subsequent hydrolysis give 1,5-diketones, for example, amine but 3-ene 2-on methyl vinyl ketone, 2,3-oxobutyl cyclohexane 1-on A15-diketone. Assigning formal charges on intermediates and other ionic species. Average electron theory. Definition of formal charge. Lewis structures frequently contain atoms that bear a positive or a negative. If the molecule as a whole is electrically neutral, the sum of the positive charges must be equal to the sum of the negative charges, for example. Thus, formal charges may be defined as the positive and negative charge which must be assigned to certain atoms within the molecules to completely describe the Lewis structure. The formal charge on any atom within a molecule and hence on the ion and intermediate as a whole can be easily calculated with the help of average electron theory. Average electron theory. According to average electron theory, the central atom in a covalent molecule is surrounded by two types of electron pairs, shared pairs and lone pairs. The shared pairs are also called bonding electrons, while lone pairs are called non-bonding electrons. The average number of electrons on the central atom depends upon the number of bonding and non-bonding electrons around it. Whereas bonding electrons are divided equally between the bonded atoms, the non-bonding electrons are assigned to the atom on which they reside. In other words, while calculating the number of average electrons on the central atom, half of the bonding electrons are added to the non-bonding electrons. Number of average electrons. Half number of bonding electrons plus number of non-bonding electrons. If the number of average electrons thus calculated is less than of neutral atom, then the atom is assigned a positive formal charge equal in magnitude to the difference between them. Conversely, if the number of average electrons on the central atom is more than that of the neutral atom, then the atom is assigned a negative formal charge equal in magnitude to the difference between them once the formal charges on each atom of the molecule have been calculated. The arithmetic sum of all the formal charges gives the net charge on the ion as a whole. Now the number of electrons on a neutral atom is equal to the number of electrons in the valence shell, 4 in case of C, 5 in case of N, 6 in case of O and 7 in case of halogens. Therefore, formal charge on atom, number of valence electrons, number of average electrons, number of valence electrons minus half into number of bonding electrons, number of non-bonding electrons. If we represent covalent bonds by lines and non-bonding electrons by dots, the above equation may be rewritten as formal charge on an atom is equal to number of valence electrons minus lines plus dots. Let us now apply the above theory to calculate formal charges on reactive intermediates such as carbocations, carboanions, free radicals, and carbenes. Methyl carbocation. The incomplete Lewis structure of methyl carbocation is CH3. Formal charge on carbon is equal to number of valence electrons minus half into number of bonding electrons minus number of non-bonding electrons is equal to plus 1. Thus, the complete Lewis structure of methyl carbocation CH3. Methyl carbocation, the incomplete Lewis structure of methyl carbanion CH3. Formal charge on carbon 4 minus half is equal to minus 1. Thus, the Lewis complete structure of methyl carbanion is CH3. Methyl free radical. The Lewis structure is methyl free radical is CH3. Formal charge on carbon is equal to 0. Thus, the complete structure of methyl free radical is the same as written above. Methylene. The Lewis structure of methylene is CH2. Formal charge on carbon 4 minus half into 4 minus 2 is equal to 0. Thus, the complete structure of methylene is the same as written above. Nitronium ion. The incomplete Lewis structure of nitronium ion. Formal charge on each O atom 6 minus half into 4 minus 4 is equal to 0. Formal charge on N atom plus 1. Thus, the complete structure of nitronium ion. To illustrate these rules, further consider a molecule of diazomethane CH2NA2 which can be written as a resonance hybrid of the following three Lewis structures. But these structures are not complete since the formal charges on some of the atoms are missing. Let us now calculate the formal charge on each of the atom in all the three Lewis structure. Lewis structure 1. Formal charge on carbon is equal to minus 1. Formal charge on central nitrogen plus 1. Formal charge on terminal nitrogen 0. Thus the complete Lewis structure. Lewis structure 2nd. Formal charge on carbon 4 minus half into 8 is equal to 0. Formal charge on central nitrogen plus 1. Formal charge on terminal nitrogen minus 1. Thus the complete Lewis structure 2nd is. Lewis structure 3rd. Formal charge on carbon is equal to minus 1. Formal charge on central nitrogen 0. Formal charge on terminal nitrogen plus 1. Thus the complete Lewis structure 3rd is. Thus diazomethane is a resonance hybrid of the following three Lewis structures. In each of three Lewis structures written above, the sum of the formal charges is 0. Therefore, diazomethane as a whole is an electrically neutral molecule. Methods of determining reaction mechanism. The mechanism of a reaction implies the path which the reactant follows on their way to products. Since many chemical reactions proceed very rapidly, it is not possible to follow the reaction path directly, and hence our knowledge about reaction mechanisms is mostly based upon indirect evidence. After characterizing the product, a number of mechanisms consist with all the experimental observations are proposed. In a host of the cases, new experiments are carried out to eliminate some of these mechanisms. If such eliminations lead to only one mechanism, then it is said to be the established mechanism of the reaction. In general, then the proposed mechanism for a reaction should be energetically favorable, should account for initial experiment observations, and third, must be consistent with the mechanisms of the analogous reactions. A number of methods are used to determine the mechanism of a reaction. This includes product analysis, identification of products, detection and isolation of the intermediates, isotopic labeling, isotope effects, kinetic studies, and stereochemical studies. All these methods are briefly discussed below. It may, however, be noted that it is not necessary to apply all the methods to determine the mechanism of a partial reaction. Product analysis. The first step in investigating the mechanism of a reaction is the identification of product and determining the relative amounts. To illustrate this point, let us consider the following reactions. The hydrolysis of two isomeric alkyl chlorides, first and second, yields a mixture of 85% of a tertiary alcohol and 15% of a primary alcohol. Since the composition of the products remains to be the same in either case, therefore the hydrolysis of these compounds occurs through a common intermediate. 3-chloro-3-methylbutene, 2-methylbute-2-ene 2-ol, 4-chloro-2-methylbute-2-ene, 3-methylbute-2-ene 1-ol. Etoxemes on treatment with an acid H2SO4, H3PO4, PCl5, SOCl2, etc. undergo Beckmann rearrangement to give the corresponding substituted amides. Product analysis has revealed that during this rearrangement, it is always the group anti or trans to the OH group which migrates and has thus helped to determine the mechanism of the Beckmann rearrangement. Thus, sinalkyl aryl ketocene and aryl acid amide, anti-alkyl aryl ketoxime and alkyl acid amide. Crossover experiments. Crossover experiments are quite useful in determining whether a particular reaction is a one-step or a two-step process. In these experiments, the same reaction is carried out with a mixture of two similar but non-identical reactants, and the product thus obtained are analyzed to illustrate the role of crossover experiment in determining the mechanism of organic reaction. Let us discuss Frey's role of rearrangement of ester 6th and 7th, which involve migration of the alkyl or aryl group from the oxygen atom to the benzene ring. These add two esters on treatment with anhydride AlCl3 under similar conditions undergo rearrangement at approximately the same rate to give the product 8th and 9th respectively. For toluol benzoate, 2 hydroxy 5 methyl benzophenone, 2 chloro 4 methyl phenyl acetate, 2 hydroxy 3 chloro 5 methyl acetophenone, 2 hydroxy 5 methyl acetophenone, 2 hydroxy 3 chloro 5 methyl benzophenone. If the same reaction is now carried out with the mixture of these two esters 6th and 7th under similar conditions, two possibilities arise. If the reaction occurs concentratedly or in one step, the ester 6th will always give the ketone 8th, while the ester 6th will always give the ketone 9. If, however, the reaction occurs in two steps, then the migrating group C6H5CO in ester 6 and CH3CO group in ester 7 must become free during the course of the rearrangement, and hence crossover product 10th and 11th must also be formed in addition to the expected product 8th and 9th. In actual practice, when the same reaction was carried out with the mixture of these two esters 6th and 7th, the crossover product 10th and 11th were also isolated in addition to expected product, thereby confirming the Frey's rearrangement in a two-step process. Detection and isolation of intermediates. Many organic reactions occur through formation of intermediates which may either be stable or unstable. The stable intermediates are isolated and then characterized. The unstable intermediates, on the other hand, are either detected by spectroscopic method or are isolated by trapping them with reactive substrates as discussed below. Isolation. If the intermediates are stable, they are usually isolated by stopping the reaction before it is completed or by using relatively milder conditions. For example, 3 intermediates and bromoamide, it's an ion, and the isocyanate have been isolated in the Hofmann bromoamide rearrangement of primary amides to primary amides on treatment with Br2KOH. Primary amide and bromoamide isocyanate. Thus, any proposed mechanism for this rearrangement must account for the formation of all these intermediates. Detection. Unstable intermediates are often detected by spectroscopic methods. For example, intermediacy of carbocation intermediates in SN1 unimolecular nucleophilic substitution and E1 unimolecular elimination. Reaction has been stabilized by nuclear magnetic resonance NMR spectroscopic. Similarly, carbocation intermediates such as 7A electrophilic substitution reactions have been characterized by their NMR and electronic spectra. Acetylene free radical intermediates can be detected by electron spin resonance ESR spectroscopy. Trapping. Unstable intermediate can also be characterized by trapping. For this purpose, the reaction is carried out in presence of a compound with which it is known to react rapidly. Carbene formed during photochemical decomposition of diazomethane can be trapped as cyclopropane derivative when the decomposition is carried out in presence of cyclohexane diazomethane carbene. Benzene formed during decomposition of benzene disonium 2 carboxylate can be trapped by anthranes to form tryptophan. Carbocations are trapped by reacting them with nucleophiles. For example, the carbocation formed during the addition of Br2 to ethylene can be trapped by a number of nucleophiles such as INO3H2 etc. Ethylene carbocation. Free radicals can be trapped by carrying out the reaction in presence of nitric acid oxide with which it is known to react rapidly. For example, free radical formed during thermal decomposition of acidic butyronitrotol is trapped by nitric oxide to form hydroxylamine derivative. Isotopic labeling. The mechanism of many reactions can be studied by using molecules in which an atom is substituted by its isotope. For example, hydrolysis of esters. The mechanism of hydrolysis of an ester, whether it involves alkyl oxygen or alkyl oxygen fission, can be solved by hydrolyzing anamyl acetate in H2-etino. Anamyl acetate. Since the hydrolases yield an unlabeled alcohol and a labeled acid, hydrolysis of esters involves alkyl oxygen rather than alkyl oxygen fission. Cannizzaro reaction. Cannizzaro reaction involves transfer of a hydrogen from one molecule to other. The question whether the hydrogen which gets transferred comes from water or the aldehyde can be solved by carrying out the reaction with deuterated benzaldehyde C6H5CDO instead of benzaldehyde. Deuterated benzaldehyde, deuterated benzyl alcohol. Since the deuterium is exclusively located on the carbon atom of the benzyl alcohol carrying the hydroxyl group, the possibility of exchange of hydrogen with the hydrogen atom of water is ruled out. Thus, there is a transfer of deuterium or hydrogen from the carbonyl group of one molecule to the other, and during this transfer, deuterium or hydrogen never gets detected. A plausible mechanism consistent with the above observation can be visualized as follows. Further support to the above mechanism comes from the observation that when the reaction of benzaldehyde was carried out in D2O, the recovered alcohol contained no alpha deuterium, indicating thereby that the hydrogen comes from another molecule of aldehyde and not from the solvent. Nucleophilic substitution benzene mechanism. When chlorobenzene is treated with NaNH2 in liquid NH3, aniline is formed. The mechanism of this nucleophilic substitution reaction involves a benzene intermediate as shown in section 2.13.2 on page 89. This mechanism is supported by the observation that when chlorobenzene is which chlorine is attached to labeled carbon C14, two types of anilines are produced, one in which the NH2 group is attached to C14 while the other in which NH2 group is attached to a C12 carbon next to the C14 carbon as shown below. Isotope effects. While discussing isotopic labeling as a tool to investigate reaction mechanism, we have made an important assumption that there is no difference in a chemical behavior of different isotopes and hence the chemical properties of the compounds are not quantitatively changed when a particular atom is a compound is replaced by its isotope. However, in actual practice, isotopes, because of their different masses, do affect the rates of the chemical reactions. The variations in the rate of reaction when an atom in a compound is replaced by its isotope is called isotope effect. Usually it is very small. However, if the replacement of an atom by its isotope is involved in the rate determining step of the reaction, the magnitude of the isotopic effect may be quite large and is called primary isotope effect. Since the mass of a deuterium atom is double and that of a tritium atom is triple than of a hydrogen atom. Therefore, the magnitude of the primary isotope effect is the greatest when a hydrogen atom is replaced by a deuterium or tritium. It is usually expressed in terms of the rate ratio or respectively. The value of this rate ratio is always greater than 1, which means that the compound containing hydrogen reacts faster than that containing deuterium or tritium. Typical values for hand. The reasons for the primary isotope effect is the bond dissociation energy of the CD bond is more than that of CH bond and even greater for the CT bond. Therefore, the energy of activation for cleaving the CD bond would be much greater than that of CH bond, and hence the rate of the reaction involving CD bond cleavage will be slow. It may however be noted here that if the CD and CH bond cleavages are not involved in the rate determining step of the reaction, then the rate of the reaction will be hardly affected when hydrogen is replaced by isotope DOT. Most of the studies of isotope effect have been carried out using deuterium and not tritium because it is more easily available and also because tritium is radioactive. Primary isotope effect and reaction mechanism. Primary isotope is a powerful tool in determining the mechanism of many reactions. For example, dehydrohalogenation of isopropyl bromide. The rate of dehydrohalogenation of isopropyl bromide with sodium ethoxide is considerably reduced when the hydrogen atom of the methyl group are replaced by deuterium. Secondary isotope effect. Deuterium isotope effect have been found even when it is certain that the CH bond does not break at all in the reaction. Such effects are called secondary isotope effect, and their magnitude is quite small as compared to the primary isotope effects. These are further classified as alpha, beta and gamma according as the deuterium atom is present at alpha, beta or Y position. Carbon at which the reaction in taking place. An example of beta secondary isotope effect in the solvolysis, hydrolysis by the solvent of the isopropyl bromide. The KH-KD rate ratio for this reaction is found to be 1.34. The most probable reason for the secondary isotope effect is hyperconjugation. This large isotope effect definitely suggests that the rate determining step of the reaction involves the cleavage of the CH bond. As such, the flowing mechanism for the above reaction is ruled out because in this mechanism CH bond cleavage is a fast step. The correct mechanism for this reaction may be as follows. Thus we conclude that it is CH bond cleavage and not CBr bond cleavage which is involved in the rate determining step of the reaction. Nitration of benzene. Nitration of benzene is an electrophilic substitution reaction. Here nitronium ion attacks the benzene ring forming a carbocation intermediate which loses a proton to give nitrobenzene. In each hexadeotrated benzene or hexatriated benzene in use in place of benzene, the rate of nitration has been found to be the same. This means that nitration of benzene does not show any isotope effect. In other words, the rate determining step of the reaction does not involve breaking of the CH. Conventionally, attack of NO2 on the benzene ring is the rate determining step while the cleavage of the CH bond is a fast step. Thus, the correct mechanism for nitration of benzene may be formulated as follows. Kinetic evidence. The kinetic evidence alone is not sufficient to determine the mechanism of a particular reaction. However, these studies give useful information about the rate determining step of the reaction. It is often possible to rule out many mechanisms simply on the basis of rate law. The most important example where kinetic studies have been useful in determining the mechanism of the reaction is the hydrolysis of alkyl halides. For example, the hydrolysis of methyl bromide shows second order kinetics. This rate slow suggests that both CH3Br and OH ion are participating in the rate determining step of the reaction. Such reactions are called SN2 reactions and occur in one step through the participation of transition state. In contrast, the hydrolysis of T-butyl bromide shows first order kinetics. Since the rate law depends only on the concentration of CH3Cbr and is independent of the concentration of OH ion, therefore rate determining step involves only CH3Cbr. Such reactions are called SNI reactions and occur in two steps. The first step involves ionization of the alkyl halide to give a carbocation intermediate. This is rate determining step of the reaction. In the second step, the carbocation intermediate is rapidly attacked by the nucleophile, giving the substitution product. Stereochemical evidence. Sometimes the mechanism of a reaction can be determined the following the stereochemistry of the reactant and the product. For example, the mechanism of nucleophilic substitution reaction SN1 and SN2 have been investigated by carrying out reactions with optically active compounds and then checking the optical purity of the products. Mechanism of SN2 reactions: hydrolysis of actively active 1-chloro 1-phenyl ethane with aqueous KOH gives racemic 1-phenyl ethanol. Racemization of the product suggests that the reaction occurs through a planar carbocation intermediate since the attack of the nucleophile on this rear carbocation can occur from both the faces front and rear with almost equal heat giving a 50:50 mixture of two enantiomers. From the above discussion, we conclude that SNI reactions occur through carbocation intermediates. Mechanism of SN2 reactions. Hydrolysis of optically active 2-bromo-octane gives optically active 2-octanol. This can be explained if we assume that attack of the OH occurs from the side opposite to the bromine atom giving first a transition state which then expels the Br ion to give the product. During this reaction, inversion of configuration occurs. This is called Belden inversion. From the above discussion, we conclude that SN2 reactions are one-step reactions in which optically active reactions give optically active products with inverted configuration. Elimination reaction. The dehydrogenation of cis-1,2 dichloroethane gives chloroacetylene 20 times faster than the corresponding trans isomer. This suggests that E2 reactions occur more rapidly when the departing groups are in trans orientation than when they are cis. Cis-1,2 dichloroethane H and Cl are trans. Chloroacetylene trans 1,2 dichloroethane H and Cl are cis.